In this video, we are going to cover the Cauchy integral formula, which is the companion to the Cauchy integral theorem, which we had seen in the previous video. So this is our overview slide, which we'll spend about 5 minutes going over before we go over each topic in more detail and more examples. And one thing I am going to say, if you need to know what is what, it's important to realize that Cauchy did a lot of work, and also Riemann and everyone else did a lot. It's like the same people who are doing work and analysis. So many formulas and theorems are named after Cauchy. For example, we had the Cauchy-Riemann conditions for analytic functions. We had the Cauchy integral theorem, which many books call the Cauchy-Gorsatz's integral theorem, and that was from our last video. And now we're going to do the Cauchy integral formula, which will also cover the Cauchy integral theorem. So it's not terrible. As I said, so now we're going to do a quick overview, 5 minutes or less, and then we'll go through each topic. So the first topic we're going to cover is a review of the Cauchy integral theorem that said if we have W is a complex function that takes a complex number, produces a complex number, it's analytic in some region of the complex plane. If we consider an integral along a closed contour C, like this path here, C, that's drawn, which lies entirely within the analytic region, then the integral along this curve is equal to 0. So this is the Cauchy integral theorem. From the theorem, one of the results is that we have this contour deformation. So a result of the Cauchy integral theorem is the contour of a complex integral can be arbitrarily deformed to an analytic region, as long as we deform it in an analytic region without changing the value of the integral. And we'll look at these 3 drawings to see why that is the case. The new thing we are going to look at is the Cauchy integral formula, and it involves the integral of f of z, where f of z is analytic everywhere inside and on a simple closed contour C, divided by z minus z naught. So f of z, z minus z naught, is not analytic at z naught because then you have a division by 0. If z naught is outside our contour, then we're in this case of the Cauchy integral theorem, and we can say the integral is equal to 0. However, if it's inside, then the Cauchy integral formula tells us how to deal with this case. So if z naught is inside, then the integral is equal to 2 pi I f evaluated at z naught. And we'll take a look at how this is derived as well as examples. One more comment, you see where this says the contour C taken in the positive sense. By the positive sense, we mean our curve goes in the counterclockwise direction, and the counterclockwise direction is considered the positive direction because it's in the direction of increasing radians or degrees. A consequence of the Cauchy integral formula is that if a function f is analytic within and on a simple closed contour C, then the values of f interior to C are completely determined by the values of f on C. And that comes directly from this integral equals 2 pi I f of z. If we divide both sides by 2 pi I, we get f at z naught is 1 over 2 pi I, the integral of c dz f of z over z minus z naught. And finally, we have the general form of Cauchy's integral formula, which is, we get that by taking the derivative of both sides of this equation with respect to z naught. And we'll go over this as well as an example. That covers our brief overview, so now we'll go back and review the Cauchy integral theorem. So the Cauchy integral theorem said if we have a complex function w, it takes a complex number, it produces a complex number. And if it's analytic in some region of the complex plane, when we consider an integral along a closed contour C, and the important thing is that the contour is closed, in other words, well, it looks closed, which lies entirely within the analytic region. That's the second thing. It's closed and it lies entirely in the analytic region. Then the integral over here is equal to C. So the integral over the closed contour of WZ is equal to 0. Our first example is the integral over C, where C is this circle of radius 1, 1 over z. So f of z satisfies the Cauchy-Riemann necessary condition, but it is the Cauchy-Riemann, remember, is not sufficient to guarantee analytic. the function also and its derivatives need to be defined, but you can see f of z is not defined at z equals 0. Since f of z is not analytic at the origin, which is in the interior of our circle, right, it's right here, we cannot use the Cauchy integral theorem. Our next example was to evaluate the integral where c is again our circle of radius 1, z squared over z minus 2. In this case, we can show that it's analytic except at z equals 2 over here. But since z equals 2 is outside our curve, we can use our Cauchy integral theorem because our z squared over z minus 2 is analytic on the curve and interior. But since c is a closed curve, that means by our Cauchy integral theorem, the integral is equal to 0. This is really such a great theorem because when you have a closed curve and you're analytic, you don't have to do anything. You just get to say equals 0. And a direct result of the Cauchy integral theorem is contour deformation. That says that the contour of a complex integral can be arbitrarily deformed into an analytic region without changing the value of the integral. And to see that, we have these three pictures. So first, and we did go over this in our previous video, but I'm just going to review it anyway. It's pretty quick. So if we consider the integral over this simple curve, which is a line, and I chose a very simple line, you could do a circle, a curve, whatever you want, but I did a line. And this line does have a direction. It goes from A to B, and the direction is given by this arrow. Now what we can do from the Cauchy integral theorem, if I take any closed curve, as long as it's analytic, that integral along this closed curve will be equal to 0. So I can simply add that to anything. In particular, I'm going to add it to my original I, which is integrated over c naught. So I'm going to add this new c, this blue curve, which is closed. And one of the things I did when I drew this curve is I intersected the curve c over a portion of my original curve c naught in black, this line in black, and I intersected it with a portion that I wanted to get rid of. And I made my direction of c at this in the intersection go in the opposite direction that my c naught goes in. So what ends up happening is for this portion where the two curves intersect, the blue and the black curves intersect, the integrals are equal except that the blue integral is going to be the negative of the black integral. So when I add these two together, this part, the portion that intersects, gets canceled out. And that's what this picture is here. I've canceled out this middle intersecting portion. So I've deformed my curve. And as we had talked about in the last video, you can deform it arbitrarily. And as long as your curve is in an analytic region, the value of the integral will remain the same. And if you think about it, well, it makes sense, but it's actually still quite surprising. Next, we're going to derive this Cauchy integral formula that says if f is analytic everywhere inside and on a simple closed contour c, the contour c taken in the positive sense, then the integral over c of f of z, so it's f of z that's analytic, divided by z minus z naught. So you can see f of z over z minus z naught is no longer analytic at z naught because you have division by 0. If z equals z naught, you have division by 0. Then the Cauchy integral formula, it gives you 0 if z naught is outside of c, and that's just coming from the Cauchy integral theorem over here. But if z naught is inside c, we have this formula now. And this is what we're going to derive next. So I have Cauchy's integral formula here for your reference. And we want to derive this formula here for the integral over c of f of z over z minus z naught. So that's this integral here we're trying to derive the formula for, where f of z is analytic everywhere, and c is a closed contour that does not include z naught. And I'm going to include my picture here. So C1 is a closed contour, and I should put C1 over here. C1 is a closed contour, and f of z is analytic everywhere, and this is f of z, not f of z over z minus z naught, but f of z is analytic everywhere, and the closed contour does not include z naught. So we know f of z is analytic everywhere, but if we look at the denominator, so 1 over z minus z naught, that is analytic everywhere except when z equals z naught, because at z equals z naught we have division by 0. But we also know that C1 does not include Z naught. So we can use Cauchy's integral formula, Cauchy's integral theorem, which I copied from our review over here. That will then tell us that our integral over C1 is going to equal to 0. So I'm going to get rid of the Cauchy integral theorem here just to give myself some space. But I have my conclusion. Since C1 does not include Z equals Z naught by Cauchy's integral theorem, our integral then over C1 is equal to 0. Next, I want to consider another integral I2 where C2 encloses Z naught and also C1. So I have the drawing here. So my integral C2 dz f of z, z minus Z naught. And now we want to note now, since f of z over z minus z naught is not analytic at z naught, we can no longer use Cauchy's integral theorem. But we're going to use some contour deformation. For now, it may not be immediately clear why it's going to help us, but just take my word for it. It will. So we can deform the contour, our C2 contour, until it is an infinitesimal circle of radius epsilon centered at z naught without affecting the value. So now, for just considering C2, we just want to shrink it around z naught. And because it's analytic over here, the C1, we don't really have to include C1 because it's 0 anyway. So everywhere it's analytic, it doesn't contribute anything to the integral. So we're just going to shrink down C2 so it barely circles z naught. And now I'm going to consider this small little circle, which, I didn't make infinitesimally small because I need to draw it and notate it. I'm going to call that C0. So we're going to consider the integral, the limit as epsilon approaches 0 of C0, so epsilon is the radius of this circle, dz f of z over z minus z naught. So we're going to take a closer look at this integral. This is theoretically a circle. Its radius is epsilon, and epsilon is going towards 0. Remember, we want it to be infinitesimal radius, epsilon, centered at z naught. And I didn't really center this at z naught, but just pretend for now. Okay, so here's my better picture of C0. Our radius is epsilon, and z naught is our center. So we're going to use phasors, which are essentially vectors in the complex plane, but what a cool name, to study the integral, I2, of over C0. So here is my drawing. I kind of moved it up so I could draw my phasors. So here's my circle, my C0 contour. I have my Z naught. So Z naught is the center, but I'm going to represent it with this vector, my phasor, Z naught. And then here's a point Z on my contour, and I'm going to represent it with a phasor Z. And my epsilon is my radius, and then there's an angle theta to get to my Z angle point. And then I also have this I guess it's another phasor between Z and Z naught, which is Z minus Z naught. And so this goes from the direction Z naught to Z. And I'm looking at my integral over C0 as the limit of epsilon approaches 0 dz of f of z over z minus z naught. And I want to remember that z naught lies in the contour C0. Now, since z lies on the contour of this circle, then we can write our phasor z minus z naught. Well, that's simply equal to our polar coordinates, or our exponential representation of this vector, which is equal to epsilon, because it has a radius of epsilon, e to the I, and then phi, where phi is the angle between the x-axis and our phasor, z minus z naught. Now, since on the curve C0, epsilon is constant, so dz is equal to, I can use this over here, I can add z naught to both sides, but when I take dz, the constant z naught is going to go to 0, so dz is equal to, then taking the derivative of this, is going to be the derivative with respect to phi. I'm going to carry my I, so I have my epsilon, it's a constant, so it sticks around, e to the I phi d phi. Which means I can now rewrite my integral I2, the limit as epsilon approaches 0 of the integral over C0 dz f of z, z minus z naught, as the limit as epsilon goes from to 0. Our limits of integration for phi is 0 to 2 pi. That'll give us the entire circle. And now we have our dz, which is I epsilon e to the I theta d phi, which is over here. And then last we need f of z, and I'm going to write z as our epsilon e to the I phi plus z naught, just adding z naught to both sides of the equation, divided by z minus z naught is epsilon e to the I phi. So this is our integral in terms of phi. We can pull out an I since it's constant. What else? This here is going to cancel with this here. So we're going to be left with our I limit as epsilon approaches 0, 0 to 2 pi, and we're left with d phi f of z plus epsilon e to the I phi. And then one other simplification, as epsilon approaches 0, this z naught plus epsilon e to the I phi, as epsilon approaches 0, this term also tends to go away. So we're going to be left with I2, it approaches I, limit as epsilon approaches 0, 0 to 2 pi, we're left with d phi f of z. So I'm going to write this, since this epsilon approaches 0, I'm just going to write this as I2 is equal to I times f of z naught. That's not an if, it's not a conditional, but f, and then we have integral from 0 to 2 pi d phi, which is just phi evaluated at 0 and 2 pi, so we're going to get 2 pi I f of z naught. So this is what our integral I2 is equal to. So now finally, we can write our integral, which was over here, dz f of z, z minus z naught, equals 2 pi I f of z if z naught is inside C, and 0 if z naught is outside C. And that is our Cauchy integral formula. So let's do some examples. So our first example is to integrate over the contour C, z over z minus 1, where c is given by the absolute value of z is equal to 2. So that's a circle of radius 2. And here, our z naught is equal to 1. That's where our f of z over z minus z naught is not defined. So I have this here, f of z. Now remember, we want it in this form. F of z is equal to z. Our z minus z naught, well, that's z minus 1. That means z naught is equal to 1. So z over z minus 1 is analytic everywhere except at z equals 1, which is in the interior of C. So that means we can't use the Cauchy integral theorem, but we can use this part of the integral formula. So by the Cauchy integral formula, this integral is equal to 2 pi I f evaluated at z naught, which is equal to 1, which is 2 pi I, and f is equal to z, so f of 1 is equal to 1. So our final answer is 2 pi I. And one thing I'm going to say, so many answers in complex analysis is 2 pi I. Also, so many circles. This is where mathematicians learn how to draw circles, although mine's a little lopsided. Our next example, integral over c. C is our same curve, our circle of radius 2, z over 9 minus z squared, z plus I. And the first thing to notice is you want to get this function here to be in this form over here, some f of z over z minus z naught. So you want z minus z naught on the bottom, and so you need to manipulate this algebraically till you're left with only z minus z naught on the bottom. Here you have a 9 minus z squared. You don't want that on the bottom because that looks nothing like z minus z naught. There's a squared term. This looks almost like z minus z naught. So we're going to work with this to be our denominator. So I should back up a little bit, and I should say that z over 9 minus z squared, z plus I, is analytic everywhere except at z equals plus or minus 3, where this would give us a 0 on the denominator, and z equals minus 1, where this factor will give us a 0 in the denominator. And our z equals plus or minus 3, that's outside c, so that gives us no problems at all. We could just ignore that. But z minus I is inside c, it's right over here. And so that is going to give us problems. Or actually, it's not that it gives us problems, it's what prevents us from using the Cauchy Integral Theorem. But anyway, as I said, we can't use the theorem, but we want to use the formula, and we want to get our function over here that we're integrating into this form. And again, our z squared, we don't want this in the denominator because it does not look like this. There's no squares, no powers here. But our z plus 1, that looks promising to stay in the denominator. So what we're going to do is on the numerator and denominator, divide both by 9 minus z squared. So that's the first thing I do. So on the numerator, I have z over 9 minus z squared. And the denominator, I still have z plus I. And I want it in the form z minus z naught. So I'm just going to make it z minus negative I. So now you can see I have this in the correct form to use the Cauchy integral formula. So in particular, using this into our form that we can use for the Cauchy integral form, so we made f of z now is equal to our z over 9 minus z squared, and then our z naught is equal to negative I. And now I can plug into my formula. So I have my integral of z over 9 minus z squared z plus I is equal to, it's going to be 2 pi I times f of z naught. So 2 pi I times f, and z naught is equal to minus I. So it's 2 pi I times, and I'm going to plug in minus I into f of z, which is minus I over 9 minus z squared. So minus I, 9 minus I squared, and when I simplify this, I get 2 pi I times this negative I divided by, this becomes minus I squared becomes a positive 1, but no. Minus I squared becomes a positive 1, so 9 minus 1 should give me 8, so this should be pi over 4. Oh wait, I did this wrong. The minus I squared, so the minus 1 squared gives us a positive 1, but I squared gives us a minus 1, so this becomes 9 plus, or minus 1, or 9 plus 1, so we get a 10 on bottom, which is how I got pi over 5 for my final answer. There are two more things that fall directly out of this Cauchy integral formula that we should cover. And again, I moved up the Cauchy integral formula here for your reference. And the first consequence of the Cauchy integral formula is if a function f is analytic within and on a simple closed contour C, then the value of f interior to C are completely determined by the values of f on C. To see this, let's assume that z naught is inside C, and we want to evaluate f of z naught. We have our Cauchy integral formula that this integral on C of f of z minus z naught is equal to 2 pi I f of z naught. We can divide both sides of this equation by 2 pi I, and then over here this will cancel out. And then we're left with the formula for f of z naught. It's equal to 1 over 2 pi I integral over C of f of z minus z naught. Again, this is a formula for f of z naught when z naught is inside the circle, and it's completely determined by what happens to f of z over z minus z naught on C. So I'm just going to write that formula here. If z naught is inside C, then we have this formula for f of z naught. Again, totally from this Cauchy integral formula, just divide both sides by 2 pi I. The next thing we have is the general form of Cauchy's integral formula, and this is the general form. To derive that, we're going to start with the form we have here, f of z is equal to 1 over 2 pi I integral over c f of z, z minus z naught. I can take the derivative of both sides of this equation with respect to z naught. So on the left-hand side, I have df z naught, z naught is equal to 1 over 2 pi I, the constant just stays, integral of c dz, f of z, since f of z is not dependent on z naught. But then I take the derivative of my z minus z naught raised to the negative 1. So instead of putting it as a fraction, I wanted to raise it as a negative exponent. Then taking the derivative with respect to z naught, that means the negative 1 comes down, and I have to subtract from this exponent, so I have minus 2. Times the derivative of what's inside with respect to z naught gives me another negative 1. So that's going to give me a plus over here, which then gives me a final answer of df of z naught dz naught is equal to 1 over 2 pi I integral of c dz f of z over z minus z naught squared. I can generalize this. I can take the nth derivative, and this is the form I will get. So I have the nth derivative of f evaluated at z naught is equal to n factorial over 2 pi I integral of f of z over z minus z naught raised to the n plus 1. And we will do an example of using this general form of Cauchy's integral. So we have the integral over c. C is the circle of radius 1, and I've drawn that here, dz of e to the 2z over z to the 4th. So now we can look at this and we can see where it's going to be difficult to get this form, if not impossible. But what we do see is we have something sort of this form, z minus z naught, n plus 1, where n is equal to 3, because 3 plus 1 would give us z to the 4th. In a previous example, we were able to divide out part of this numerator, one of the factors of the numerator, in which case then we were able to get an f of z over a z minus z naught, the z naught being a negative z naught. But you can see if we look over here at our current example, we can't just divide by z over 4, the numerator and the denominator, because we're just going to end up with the same fraction, right? If I divide the numerator by z over 4 and then divide the denominator, I'm just going to get 1 on bottom, and so I'm still left with e 2z divided by z over 4. So, this, I don't see a way to convert this to this form, but I can see how this form will convert to this other form, this general form of Cauchy's integral formula. So I'm going to go ahead and write or note that I'm going to use the general form of Cauchy's integral formula, which looks like this. And I want to look at my 1 over z to the 4th. I want to get it looking like 1 over z minus z naught to the n plus 1. So this is equal to z minus 0 to the 3 plus 1. And then my f of z, what's on top, is simply e to the 2z. And so now I'm all set up and ready to go with my formula. And on this left-hand side, I need to take the nth derivative of f, my function f over here, e to the 2z, evaluated at z naught, and z naught being 0. So the first derivative of my f is going to be 2 times e to the 2z. My second derivative over here of my f is going to be then taking the derivative of 2 times e to the 2z, I'm going to get 4 e to the 2z. And finally, my third derivative is going to be 8 e to the 2z. And now I can plug in. Now my integral of dz e to the 2z, z to the 4th, is going to be equal to, I'm going to put this on the other side of the equation, 2 pi I over n factorial, my dn f of z naught over dn, the nth derivative of f evaluated at z naught, which is 2 pi I over 3 factorial. Remember, my n is equal to 3. And then my nth derivative, my third derivative. So that's 8e to the 2z naught. And then I plug in my z naught, which is 0, so that gives me 1. So I have 2 pi I over 3 factorial times 8, which is equal to 8 pi I over 3. To review what we have gone over, we looked at the Cauchy integral formula, and we started by reviewing the Cauchy integral theorem that said if we have a function, a complex function, which is analytic in some region in the complex plane, if we have a closed contour C, which lies entirely within the analytic region, then this integral over C of W over C will always equal to 0. That was the Cauchy integral theorem. From the Cauchy integral theorem, a direct consequence is we have this contour deformation that says the contour of a complex integral can be arbitrarily deformed in an analytic region without changing the value of the integral. And then the main part of our video, the new part, was the Cauchy integral formula, which is let f be analytic everywhere inside and on a simple closed contour C. And C is taken in the positive sense. In other words, the direction is in the counterclockwise direction and it's closed. Then the integral over C of f of z divided by z minus z naught is equal to 0 if z naught is outside C, and that comes directly from the Cauchy integral theorem, or if z naught, and we see this is where our f of z minus z naught is no longer analytic. So if z naught is inside C, then our integral will be equal to 2 pi I f evaluated at z naught. And two consequences is the first one is f is analytic within and on a simple closed contour C, then the values of f interior to C are completely determined by the values of f on C. And this is a direct consequence of this part of the Cauchy integral formula. We just divide both sides of the equation by 2 pi I. And finally, by taking the derivative of this Cauchy equation with respect to z naught, we get the general form of Cauchy's integral formula. So that's it for this video. Thank you for watching.